go. So the next talk will be about CCR, not credence clearwater revival, but conditional contextual refinement, and it will be given by Youngju. The floor is yours.
Yeah, thank you. Sorry. I'm Youngju, and today I'm going to talk about conditional contextual refinement, which is a result of this beautiful collaborative effort with these all beautiful people. And conditional contextual refinement, or CCR for short, is a new theory that fully fuses the benefits of two very successful yet separate approaches in form verification, namely separation logic and contextual refinement. So, separation logic and contextual refinement are very different in nature, and they offer incomparable benefits. Let me tell you how they differ. They have a different notion of specification. The former uses Hoare triple, and the latter uses an abstract program. They offer a different notion of composability. The former decomposes state into multiple pieces, and the latter decomposes verification itself into multiple steps. And as a consequence, they offer a different form of proof reuse. The former allows its proofs to be used in different spatial contexts via the famous frame rule, and the latter allows these intermediate refinements to be reused when one comes up with a new implementation. Okay, so each side has these complementary benefits, and let's nail down what exactly they are. First, separation logic allows conditional specifications, saying that the Hoare triple assumes its precondition and asserts that it satisfies its postcondition after the execution. This means, for example, you can have a nice specification for binary search, assuming that the given pointer is pointing to a sorted list. Moreover, separation logic gives the modular reasoning principle for shared states via separating conjunction. Separating conjunction enables the well-known frame rule, and it allows reuse of the specification in different spatial contexts. In refinement, on the other hand, we do unconditional verification. For example, the gold standard definition for refinement is contextual refinement, and it basically says that the implementation behaves the same as the abstraction under an arbitrary context. And quantifying over such an arbitrary context means that we cannot impose fine-grained conditions on it. On the other hand, refinement does offer one major benefit, namely transitivity. Transitivity allows incremental verification, which means one can verify a module in a stepwise manner with multiple intermediate modules, M1 to Mn here. Then, each refinement abstracts only a certain aspect of the implementation, thus giving a nice separation of concerns between these refinements. Such an incremental verification has shown to be useful, most notably in CertOS project, and they used a notion of refinement of certified abstraction layers, and transitivity was its killer feature. So transitivity also allows proof reuse between different implementations, as mentioned. For example, if one comes up with a slightly tweaked implementation I prime, it suffices to prove that I prime refines some intermediate abstraction, Mk, to deduce that I prime refines A. In contrast, separation logic does not have this notion of transitive composition. So given these complementary benefits, our goal is to have the best of both worlds. And surely, we are not the first to consider this problem. There is already a bunch of research in the category of relational separation logic. In relational separation logic, Hoare triples are extended to Hoare quadruples, which relates two programs under separation logic pre- and post conditions. While the Hoare quadruple itself is still not transitive, there is an adequacy theorem which turns the Hoare quadruple judgment into a refinement. And by using adequacy, you gain access to transitivity. However, once you have switched to the refinement, you again lose the ability to rely on separation logic conditions and its reasoning principles. So, to summarize, while relational separation logic spans the benefits of the two, these benefits are still kept separate. What is more desirable is to have a notion that enjoys these benefits at the same time. So let us explore what this means with an example. We start with refinement, and on the left, we have a module which simply implements a simple key value storage. And this module private variable named data stores the pointer pointing to a location in memory which physically stores the contents. This module private variable is completely hidden from the outside. Then the intended usage of this module is that one first calls the init function with the size of the map to initialize the storage in memory. And after the initialization, one can use the functions get and set to load and store values from the map. This implementation is abstracted to the module on the right. Here, instead of storing the map data, map contents in memory, the module maintains a mathematical function named map to store its contents. Here, the get and set functions do not access memory, but just act directly on the mathematical data. Now, the good thing about the refinement approach is that, as I already said, we can establish such a refinement via multiple smaller refinements. For example, we can separate the refinement into 2 steps so that one can just first abstract the memory, and the next refinement does the rest of the job. We will come back to these steps pretty soon. But however, there is one big problem with this approach. That is, the refinement does not even hold at the first place. For example, suppose init is called twice, then the left and the right program behave differently. On the left, the data gets wiped, and on the right, it does not. So in order to make this refinement hold, we need a way to impose the condition that init gets called at most once and before any operation is called. A natural way to express conditions like this is through the language of separation logic. So let us take a look. With separation logic, we can give specifications for the map module as follows. First, see that the precondition of init requires a token called pending. This token is exclusive, meaning that there is only one token in the execution of the whole program, which gets consumed when init is called for the first time. This, in turn, means that init cannot be called more than once. Next, see the postcondition of init. Right after the initialization, every key in the map has value 0. We can see this in the postcondition. Here, k points to v means that the key k is currently storing the value v in the map. These points to assertions are then taken as preconditions by the other operations, thus ensuring init is called first. So to sum up, if we can use stateful pre and post conditions, we can make sure init is called at most once and also before any other operation is called. Therefore, it will be very useful to combine refinement with this power of separation logic. And this is precisely the key contribution of this work, a new notional refinement called CCR, Conditional Contextual Refinement, that allows one to rely on separation logic conditions while proving contextual refinement. Here, S is a collection of separation logic conditions indexed with function name. Then, when proving the refinement between I and A, CCR imposes the conditions in S for each function. Also, as we will see shortly, CCR enjoys the benefits of separation logic and refinement at the same time. Our theory is fully formalized in COP, and we evaluate CCR through various challenging case studies, which involves features like shared memory, mutual recursion, function pointers, non-termination, and system calls. Our framework is ready to use in the sense that it provides an end-to-end verification result down to assembly using ComCert, and we also provide an easy way to extract the programs into OCaml and execute them by using interaction trees. Let us revisit our motivating example and see how CCR handles it. Recall the problem was that contextual refinement between the implementation and the abstraction does not hold. Now in CCR, the refinement does hold because we are proving the refinement under the conditions given in this specification. And also, as promised, we can establish such a refinement in a stepwise manner. And this means CCR indeed enjoys the benefits of refinement and separation logic at the same time. To get a better sense of what this means, let us briefly go through the example. In the first refinement, we abstract memory into a mathematical function. And here, we crucially rely on the fact that init gets called at most once, which is ensured by the pending token in the precondition. Then, in the second refinement, we prove that the specification, we prove the final full specification independently of memory. So as you can see, CCR enjoys the benefits of both separation logic and refinement at the same time. It combines stateful pre and post conditions with transitivity. Okay, now we know what CCR can do. Let me explain the key ideas behind it. The first key idea is using wrappers, and let's see what that means. We define the notion of conditional refinement using unconditional refinement and to be specific, contextual refinement. And we integrate the conditions in the form of a wrapper that wraps the abstraction module A. In other words, we operationalize separation logic conditions and enforce them to hold dynamically during the execution. What is good about this approach is that we can piggyback on all the existing benefits of unconditional refinement. It's simple, universal definition, and its various properties like transitivity and horizontal compositionality. So in CCR, the purple conditions that we have seen before are inserted by the wrapper in the form of these purple operationalized cons instructions. These instructions operationalize the conditions by enforcing them dynamically in the operational semantics. So next, let me tell you how we define these operationalized cons. And I will explain it in a two-step. I will first explain a simplified version of wrapper, which we call stateless wrapper, that handles only Hoare logic conditions. Then we extend it to a stateful wrapper that handles separation logic conditions. To explain the stateless wrapper, let us take a look at the toy example. Here we have a simple function that computes exponentiation. And then, exponentiation. Then under the precondition that n is non-negative, we abstract the implementation to an abstraction that directly returns x to the power of n. As mentioned, under the hood, these conditions are automatically inserted by wrapper. Intuitively, we want to assume the precondition at the beginning and assert the postcondition at the end. And we literally use the assume and assert constructs borrowed from the work on refinement calculus by Ralph Johann Bach. As the name implies, the logical rule for assume allows us to assume proposition P, and the logical rule for assert requires us to prove P. Now we consider a simple client of this module, which just calls exp with 3 and 2, and then returns the result. On the side of the client, the wrapper inserts the pre and post conditions of exp, but this time in the opposite way. Since the client module is calling the exp function, it needs to prove the precondition and gets to assume the postcondition. This way, we are ensuring that every assume is preceded by a matching assert, and later in this talk, we will see how they cancel each other out. Finally, because we can assume the postcondition of exp, we can prove a stronger refinement. In the client, we can replace R with 9. Okay, now let's see how we define stateful wrapper. And at the high level, the idea is pretty simple. Just as we use assume and assert for pure propositions, we will introduce a new version of assume and assert for separation logic propositions. To explain what it looks like, let's look at an example. Here, the main function initializes the map with size 2 and stores the value 42 at key 0 in the map. Now, recall the specification of the map module. And as promised, they are operationalized with a new version of assume and assert. Importantly, separation logic conditions are fundamentally different from pure propositions in the sense that they convey the notion of ownership, not just facts. And for instance, unlike pure propositions, separation logic propositions are not duplicable. A pending token exists only before init is called and it gets consumed by the call. But this poses a challenge. How do we operationalize the notion of ownership and transferring ownership from the caller to the callee? Separation logic propositions are modeled as pure predicates over resources. And we make use of this fact to encode assume and assert on separation logic propositions using the assume and assert that we already know. Thus, our first step is to make resources explicit. For instance, asserting the precondition of init means the underlying resource satisfies the proposition pending. And these resources need to be transferred between modules, from client to init, and back, and from client to set, and back. The key question that remains is how do we transfer them operationally? As a first attempt, let us try to pass them explicitly as arguments and return values. Sorry. Unfortunately, this approach does not work. The issue is that it breaks transitivity. To understand why, let us go back to the original transitivity example. Suppose we extend this refinement chain with resources as additional arguments, and let us focus on the get function for the moment. Then the context in the contextual refinement will pass the same resource R0 to and expect the same resource R1 from all these three modules. However, true and k points to v are not satisfied by the same resource, thus the refinement with this additional argument approach will not work. At a high level, the situation is like this. Additional data called resource wants to flow into another module, but there is a wall blocking it named contextual refinement. And here comes our second key idea, the use of dual non-determinism as a technique to implicitly pass resources. Dual non-determinism, meaning the combination of demonic and angelic non-determinism, effectively work as a backdoor that can transport data from one module to another module without changing the type of argument and return values. So we replaced the explicit argument passing before with this demonic and angelic non-determinism. And note that we are not changing the argument type as before, and we can keep working on contextual refinement. And explaining how exactly this implicit resource passing via demonic and angelic non-determinism works is beyond the scope of this talk, but I will try to give you an intuition by sticking with this Super Mario analogy. Think of the non-deterministic choices as pipes that are connected. The resource Mario can go back and forth between them without explicitly appearing as an argument. The client starts by sending a resource, R0, that satisfies pending. The map receives it, updates it to the resource, R1, that satisfies the post condition, and sends it back to the client. Client receives it, and split it into two parts, R2 and FR, where the latter will work as a frame in the sense of separation logic. And sends only R2, receives R2, and sends the updated resource R3, and receives R3. And finally, we can continue this adventure with our loyal frame that was left behind. So we have seen how to operationalize separation logic conditions in CCR. But at the end of the day, when we prove the refinement result for the whole program, we want to get rid of these assumes and asserts. To do this, we rely on a key result we call the wrapper elimination theorem. To explain this theorem, let's return to our example. Here we have the map module on the right and the client module on the left. And they have both been verified separately under the same specification S, which describes the pre and post conditions for each module. Then we link them together to get a closed program. And once we have a closed program, we can get rid of this angelic and demonic non-determinism, meaning getting rid of these pipes. This is because we are guaranteed that they will always be sequenced right after one another. And after this, the remaining assumptions and assertions directly match to each other, since every module adheres to the same conditions S. Thus, we can also remove the remaining assumes and asserts. This elimination result is formalized as a generic wrapper elimination theorem as follows. To summarize, if every module adheres to the same spec, i.e. the pipes are installed properly, the resources are matched up properly during the execution, i.e. Mario does not die from a pipe accident, and this is sufficient to get rid of these wrappers, i.e. getting rid of these pipes. So CCR is developed some time ago, and this still actively being developed. We don't consider it as just one-time project. And also, it's already having some influences on other projects. Actually, it inspired a project named Dim Sum, led by Michael Sammler, which will be presented here today at 4:45. Dim Sum uses this key idea of using dual non-determinism to tackle the multi-language semantics problem. And I would strongly encourage you to attend his talk. Thanks for listening, and I'm happy to answer any question.
Thank you very much for the talk. We have time for some questions. Yeah? Of course. Okay.
All right. So Zhongshao from Yale University. So I feel like you didn't represent the contextual refinement work in 30 course very well because we clearly have a pre-post condition for all these, spec. So I'm curious, what is the main difference compared with what we do in 30 course? And in, also in the recent papers we published in the last 2 years, which also uses the dual non-determinism and other features.
So, thanks for the question. And as far as I know, Certicos and its recent publications included does not have this notion of separation logic included. So, if you ignore separation logic and only care about Hoare logic, then the similar idea was already in the literature, including the Certicos and also coming back to the refinement calculus. So I think the main difference is the use of separation logic. And for some version of the certified abstraction layers, they do not support visual recursion very well. So that is also another difference, I think. Yes.
Can you repeat the question since there was no mic?
Yeah, I was just saying, we can implement any form of separation logic in our specialized cock-proof assistant. So I don't see why separation logic is anything special. But anyway, we can go offline. I'm just curious.
Yeah, I'm happy to have an offline discussion. Yes, thank you.
Okay, so for the manipulation of resources,
yes.
So do you use the IRIS tools or somehow?
Yes, technically, we use iris proof mode, yes. But the notion of resource itself is defined in a custom way without step indices. But we instantiate iris proof mode with our notion of resource. Yes.
Hi. So I have a question about the implicit resource passing. Do you lose anything by making this implicit?
Lose anything by making?
As in, are there any properties that no longer hold, or are you losing something?
It's hard to answer if we are losing something from making it implicit, but there is a gap between our support of separation logic with the full Fisher iris, in the sense that we don't have the notion of step indexes. So which means that we are not handling these higher order post states, and that is the major difference with the separation logic, I think.
I meant rather compared to if you had some sort of resource passing that's not explicit, for example, say linear types or something like that, something that ensures you're passing resources systematically.
So does that have the notion of transitivity? The type system is usually about it's a unary notion. So type system is usually a unary notion, and the key problem we are tackling here is so we are tackling the separation. We are integrating separation logic and transitivity at the same time. So I think that's the difference.
Thanks.
Okay, I think we have time for one very, very brief question here in the front.
Leonard Beringer from Princeton. Most separation logics only handle partial correctness with the exception of transfinite stepping things in iris. But you mentioned non-termination proofs as well. Can you say a bit how you overcome that limitation?
The usual separation logic does not handle the Leibniz properties because it has this ground on the step indexing techniques. But so we don't start with separation logic or step indexing. We start with refinement, and we integrate the separation logic conditions inside the operations matrix. We somehow find a way to operationalize them. So if you consider the traditional notion of contextual refinement, it's not strange to have this termination sensitive notion of refinement, and then we just find a way to integrate the separation logic inside this framework. So yeah.
Okay, let's thank the speaker once again.